Hello, welcome today to the third lesson on sequences and series for Year 13 Edexcel A-Level. So the first couple of lessons on sequences and series, we've looked at arithmetic sequences and then arithmetic series. Now we're going to have a look at today geometric sequences, where instead of each term being the previous add or subtract the same number, here each term is the previous one multiplied or divided by a constant term known as the common ratio. So we're going to get warmed up as ever with a few exam type questions. So here they are, 4 of them to have a go at. Press pause now, try these on your own, and when you're ready to see the solutions, press play and I'll guide you through how to come to the solutions to each one. Alright then, so let's have a look together at warm-up question 1. So here we have an Olympic javelin thrower launches, in other words throwing a javelin. The height, h meters, of the javelin above the ground is modelled by this formula, where d is a horizontal distance of the javelin from the thrower measured in meters. For part A, we need to find the horizontal distance travelled by the javelin before it strikes the ground. So when it does strike the ground, we just need to realise that the height of it, h, is going to be 0. So for A, just sub h equals 0. So we want to solve 1.8 plus 1.1d minus 0.014d squared, all equal to 0. Now we could use a quadratic formula for this, but hopefully by now you've taken my suggestion and ordered yourself one of these and have one of these already, the ClassWiz. So I'll show you how to do this on the calculator. So using the ClassWiz, here's how you do it. So you go to the menu function, so press menu here, then we're going to scroll along to get to option A, equation slash function, so press equals. Now we've got a quadratic to solve. The highest power is 2, so press polynomial, then option 2 for quadratic. Now we put in for the leading term the coefficient of the squared term. So this is minus 0.014, so minus 0.014. The d term is 1.1, so type in 1.1, and then 1.8 is the constant term at the end. Press equals and equals again. So one value is 80.17, the other value is negative. So we can see here that what we're going to be looking at here is actually the first one. So we're talking about 80.2 meters is how far it goes horizontally before it hits the ground. So d equals 80.2 meters, correct to 3 significant figures. Then part B, we're asked to provide a physical interpretation for the value of 1.8 using this model. So this 1.8. So 1.8 is the value of h when d is 0. But that isn't answering the question. When h was 0, all this would be nothing. So we'd just be left with 1.8. So when it's not travelled any horizontal distance at all, it must have been 1.8 meters in the air. And so what it's saying here is, the moment it leaves the javeliner's or javelinist's hand, it's 1.8 meters above the ground. So this is the height from which the javelin is thrown. So 1.8 meters is the height from which it was thrown. It's the height above ground that the javelin is thrown from. Anything along that line would get you the mark. Let's have a look now at warm-up question 2. So links to question 1, again this javelin thrower. So for the javelin's trajectory from the previous question, what we're asked to do here is to write 1.8 plus 1.1d minus 0.014d squared in the form a minus b brackets d minus c all squared, where a, b and c are constants to be found. So what this is saying, without saying it, is we need to complete the square. I'll show you as well how to do this afterwards using the class whiz. So without the class whiz though, what I'm going to do is I'm going to show you how to complete the square step by step. So let's start with the initial expression. Now when we complete the square, what we need to do is factorise out any leading coefficient of the squared term. So we need to factorise out this minus 0.014. So I'll leave 1.8 as it is, and this minus 0.014 I'm going to factorise out, and then put the rest of the stuff in brackets. So I'm going to minus 0.014, in fact that minus should be part of it too. Okay. So I've got d squared. Now 1.1 is obviously positive. This factorised out term is negative, so to make this pop out to be positive, which it needs to be, I need to put a minus in here. I then put the original 1.1 divided by this leading term, so that when I multiply out, this on the bottom will exactly cancel with this here to just leave me with minus 1.1. So minus times minus 1.1 will give me this positive 1.1, which it needs to be. So that's the first step. Next, what we do is we now complete the square with the stuff inside these brackets here. So we've got minus 0.014. Now d squared, we just put d in the brackets. This value here we half, so if we half it we can double the denominator essentially. So it's 1.1, double 0.014 becomes 0.028. We square all that, and then what we need to do is not leave myself enough space again, because I never do. I think I'd learn, but never mind, I'll stop complaining. So then what we need is to subtract away 1.1 over 0.028 all squared. So let's do this next. So 1.1 over 0.028, all of that squared gives 75625 over 49. Just check I've got those numbers correct. Yes, I have. And finally, we can expand back out. So I've got 1.8 minus 0.014 d minus 1.1 divided by 0.028. I'll see if that can be written in exact form, in fact, as a better fraction. Yeah, I'll write it as 275 over 7. So all I'm doing here is I'm rewriting this 1.1 over 0.028 in this form, and then if I were to do minus 0.014 times minus 7565 over 49, let's see what that gives me. So minus 0.014 multiplied by minus 75625 over 49, I get there 605 over 28, which is this awful looking number here, which I'll come to in a moment. Plus 605 over 28. So A, the constant term, will just be 1.8 plus 605 over 28. So I can, oops, not that. So I can combine this constant and that constant here to work out what A will be. So if I add to this 1.8, I get 3277 over 140. So I'll leave it in exact form. I'm going to subtract away 0.014 d minus 275 over 7 squared. And so that minus 275 over 7, that's the C term. D I've got there. And B is just the leading coefficient, which we can see is 0.014. So we've got it sorted now. Now I did say I'd show you how to do this on ClassWiz. So on the ClassWiz, what you do to complete the square is you'd realise that this leading term of the quadratic, this leading coefficient, will always be appearing here in front of the bracket. And so B, you just need to remember, B will always be this number here with the correct sign placed in front of it. So to do that on the ClassWiz, we go menu, equation / function, polynomial, degree 2, just like we did before. We type in exactly what we typed in before, so minus 0.014, 1.1, and then 1.8. Press equals, but now you go past the solutions to where it says max or min. So the max or min, this value here, we put into the brackets and switch its sign. So 275 over 7 becomes minus 275 over 7. If we press equals again, we get the constant term outside of the brackets. So if we press equals again, you see here that this number will always be this constant term here. The only thing we're not told is what the leading coefficient is before these brackets. But like I say, if you can remember that this minus 0.014, whatever it might be, will always be the same as this value here, the calculator can fill in the blanks for you, so it completes the square really, really quickly. For example, if this was plus 6d squared, this would be a plus 6 here. If this were minus a million, this would be minus a million. Anyway, part B now. It now asks us to find the maximum height of a javelin and the horizontal distance from the thrower that the maximum height occurs. By completing the square, we are essentially just looking at the turning point to tell us this. So the maximum height of a javelin will just be this constant term here. So the maximum height is 3277 over 140, which we can write in a more straightforward way in a moment. And the horizontal distance from the javelin thrower where the maximum occurs, that's just going to be this C number here. So therefore, maximum height is 3277 over 140. So what do we get here? So 3277 divided by 140. That's about 23.4 meters in the air. And then we can think about when that horizontal distance occurs. So it's going to be when it's 275 over 7 meters away from where it was thrown. So at a horizontal distance of 275 over 7, which is, let's see, 275 over 7 comes to approximately 39.3 meters away. And that's all there is to it. So let's now have a look at warm-up question 3. Question 3, we have to solve this equation. So it's one of these questions where we're not maybe sure where to begin. What I'd always say though, if you've got a trinomial, where you've got 1, 2, 3 terms equals 0 or a constant, be thinking, could this be rearranged into a quadratic? And the trick here is to look at the powers. So if the highest power is double the smaller power, chances are this is a hidden quadratic. And indeed this one is. So what we can say here, this is a hidden quadratic. And what I'd always suggest, if it is a hidden quadratic, make a substitution of big X. So let big X equal the thing which is the smaller power. So the smaller power here is this one. That one's double the power. 2x is double x. So let big X equal 5 to the x. What that gives us here is 5 to the power 2x is 5x all squared. So this thing here is actually big X squared. This thing in the middle is 7 lots of x, big X that should be, and minus 30 equals 0. Now this looks much more familiar, I'm hoping you'd realise. It's a quadratic equation in terms of big X, so how to solve this? Well, we need to factorise if possible. So can we think of two numbers that multiply to give minus 30, but when we add them together give us positive 7? With a bit of thinking, you should find that that is X, so positive 10 and a negative 3. So therefore, either big X is negative 10 or big X is positive 3. But of course, we just introduced big X to make things simpler. So re-substitute what big X actually is. So either 5 to the x is minus 10, or we've got that 5 to the x is 3, because remember we said that big X could be equal to 5 to the x in our substitution. So if we've got something here, a positive value to a power, can that ever be negative? Well, simply speaking, it can't. Okay, so if you're not sure, just try some values. If I make this really, really tiny, the power, I can get down to more or less 0. That's roughly 0, it's not ever quite 0, but it can never be negative. So in other words, this has no solutions. So I can cross this off. That just isn't ever going to work. So therefore, I'm looking at this for my solution. That isn't the final answer though, because I want it to be x equals. Here I've got what, 5 to the power x equals. So how do I solve that? Well, what I can do here is I can take logs of both sides. So it could be log base 10, it could be natural logs. It doesn't matter as long as you take logs to the same base of both sides. I'm going to take the natural log of both sides. So ln of 5x will be the natural log of 3. Now, if we've taken the log of something to the power of something else, we can bring the power to the front. So this is the same as saying x ln 5 equals ln 3. Therefore, if we divide both sides of this by ln 5, we see that x will equal ln 3 divided by ln 5. Evaluate this using the calculator, give answers to 2 decimal places, as it says, so ln 3 all over ln 5. We get here, is it 2 decimal places? Yes, 2 decimal places. So we've got 0.68. 683 to 3 decimal places, but it asks for 2, so it's going to be 0.68. Lastly, we can think about the last warm-up question, warm-up 4. So here we've got a throwback question relating to the factor theorem. So we've got f of x written as such. Given that x plus 3 is a factor of f of x, find the value of the constant b. So the factor theorem tells us that if something is a factor, then this value here, with the sign switched, will be a root. So minus 3 is a root of f of x. So in other words, if I were to input minus 3, this here will be equal to 0. So x cubed becomes minus 3 cubed. 5x squared becomes 5 lots of negative 3 squared. Bx becomes b times negative 3, and plus b, that will equal 0. So next what we need to do is just to simplify this out. Minus 3 cubed gives minus 27. Minus 3 squared is 9. 5 times 9 is 45. b times minus 3 is minus 3b. Plus b is obviously just plus b, so all of that equals 0. Simplify. So minus 27 plus 45 is 18. Minus 3b plus 1b is minus 2b overall. So 18 minus 2b equals 0. Rearrange and solve. Therefore b would have to be 9. So hopefully we're literally warmed up now. Let's have a look now at the next bit of this lesson, geometric sequences. So first of all, what do I mean by a geometric sequence or geometric sequences? Well, consecutive terms of geometric sequences are generated by multiplying the previous term by a constant, which is known as the common ratio, often just called lowercase r. So let's have a look at two different examples here. So one example for numbers are increasing, second example for numbers are decreasing. But let's examine here how we're going from one value to the next in this sequence. So let's just construct a quick table for each of these two sequences, then we can discuss. So U1 means a first term, U2 means a second term, etc, etc, and UN is the nth term. So I'm not so much interested in what the terms are, because we're told what these terms are. I'm thinking here how we go from one term to the next. So hopefully you can see here what's happening is these terms are doubling. So what I'm doing as I'm moving along is just multiplying by 2 each and every time. And 16 times 2 is 32. The next number would be 64. So this common ratio r is 2 in this case. So I'm going to write this all in relation to the first term and this common ratio. So the first term obviously is just 2, which I can just write down here. The second term, obviously you can see it's 4, but I want to write this as 2 multiplied by 2. The third term, I'm taking this 4 and times in by 2 again. So that's 2 times 2 times another 2. That's 2 times 2 squared. The next one, 16, you can think of that as 2 times 2 cubed. U5, 1, 2, 3, 4, 5. That's the first term. I have times by 2, 1, 2, 3, 4 times. That's 2 times the ratio to the power 4. So the nth term, the general term, is always going to be this first term, 2, multiplied by the common ratio, which is 2. But let's think about what the power of a ratio is each and every time. Now the first term doesn't involve a ratio at all. The second term, I'm multiplying by ratio once. The third term, I'm multiplying by ratio twice. Fourth term, I'm multiplying by ratio 3 times. The fifth term, I'm multiplying by ratio 4 times. The power of a ratio is always 1 less than the term number. And so here, for the nth term, you can see hopefully it's the first term multiplied by the common ratio to the power of n minus 1. It's 2 times 2 to the power n minus 1. Does it work here, I wonder? This is a second example. Well, for this example, we can see it looks like each term going along is being divided. So a half divided by 3 gives us a sixth. If we divide that by 3, it's 1/18th and so on. But with geometric sequences, we always need to think of it as one term multiplied to get the next. So if we're dividing by 3, what's actually happening is we're multiplying by a third. Multiply by a third again, and so on, and so on. So again, in this case, the first term, we've got a half. So I can just write this down. So the first term's a half. Second term is a half multiplied by this common ratio. We can always work out the common ratio, by the way, by taking one term and dividing by the one that comes before it. So for example here, if we did 1/6 divided by a half, we get 1/3, which is what the ratio is. As long as the terms are next to each other, you can take any two consecutive terms. It doesn't need to be the first and second. So if I took this one here, 1 over 1/62, and divided that by 1 over 54, I'd again get 1/3. That's how you can calculate directly what the common ratio is. So going back to what I'm saying here, the second term is the first term multiplied by the common ratio. Half times a third is a sixth. The third term, 1/18th, is a half multiplied by 1/3 squared. Check it if you don't believe me. The fourth term is a half multiplied by 1/3 cubed. The fifth term is a half multiplied by 1/3, 2, 3, 4 times. So again, we can generalize now. So for the nth term, we're always taking the first term, just like we did in this first example, only here the first term is a half. And then we're multiplying that by the common ratio a certain number of times. So again, you can see here the power of the common ratio is always 1 less than the term number. 1 less than 3 is 2, 1 less than 4 is 3, 1 less than 5 is 4. So generally, for the nth term, 1 less than n is going to be n minus 1. So here, specifically, for this one, the first term happened to be 2, the common ratio happened to be 2. Here, specifically, the first term was a half, the common ratio was 1/3. But of course, we can see here, with these two examples, we've got something to work with which we can now generalize. So let's generalize it. So we've got u1, u2, u3, u to the n minus 1, un, and the n plus 1th term. So we multiply by the common ratio the number of times, which is 1 less than the term number. So for term number 2, I multiply by the ratio just once. So the second term is AR. Multiply by R again. A times R is AR squared. Over here, 1 less than n minus 1 is n minus 2. And here, the nth term, this is the key result, the nth term of any geometric sequence is the first term multiplied by the common ratio to the power n minus 1. The next one would be ARN. So to put this into your notes, the nth term of a geometric sequence with first term A and the common ratio R is AR to the power n minus 1. Now we've got that result, let's have a look at some questions together. So, first question, we've got this sequence here. So find the nth term of this geometric sequence 8, 4, 2, 1, a half, and so on, and so on. So let's use this result we had before. So the nth term is AR to the power n minus 1. We need to find the nth term in the form 2 to the power y, where y is an expression in terms of n. So what's the first term here? Well, the first term is 8. The second ingredient we need is to work out the common ratio. So the common ratio we can work out by just taking one term and dividing it by the term before. So if I take 4 and divide by 8, the common ratio is 4/8, which of course is a half, which is what you can see. Each term is a previous one halved. Half of 8 is 4, half of 4 is 2, and so on, and so on. So therefore the nth term, which equals AR to the n minus 1, we can plug in now what we know. So we know A is 8, the common ratio is a half, so we can just plug this in. It's going to be 8 multiplied by a half to the power n minus 1. But we want it to be in the form 2 to a certain power. So we just need to remember that a half is the same as 2 to the minus 1. So we can replace a half with 2 to the minus 1, all to the power of n minus 1. Next, you can see that 8 is a power of 2 as well. 8 is 2 cubed, so if I replace 8 with 2 cubed, then here I've got a power of a power. So if I multiply minus 1 by n minus 1, minus 1 times minus 1 gives me plus 1, minus 1 times n is minus n. Now I've got the bases, which are both 2, and I'm multiplying a power of 2 by another power of 2. Now this goes back to GCSE. If I'm multiplying things of the same base, which have powers, I just simplify by adding the powers together. So 3 plus 1 minus n, 3 plus 1 is 4, and then just minus n. So the nth term of this one is 2 to the power of 4 minus n. Let's now have a look at a second worked example number 2. Number 2. What's the first term in this sequence to exceed 100,000? So 3, 6, 12, 24 is doubling and doubling and doubling. So again, what we need to remember here is that the nth term, un, is AR to the power of n minus 1. So we can work out A. Well, we don't even need to work it out. We've got what A is. So A is the first term, which is 3. And the common ratio, again, we just can see it's doubling. If you're not sure, just do one term divided by the one before it. So 6 divided by 3 is 2. And in fact, I'll write that down. So R is 6 divided by 3, which is 2. So each term is double the one before it. So what we're wanting is a term, n, where we're trying to find n, which just is above 100,000. So we need AR to the n minus 1. So in other words, 3 times 2 to the n minus 1 to exceed 100,000. So this is going to at some point involve logs, so we can bring this power down to the front. One suggestion we do first of all is to divide both sides by 3. So we get 2 to the power n minus 1 has to be bigger than 100,000 over 3. Now take logs of both sides. This is the key step. You could, I suppose, if you really wanted to, just keep doubling and doubling and doubling and doing like a running total, maybe like in a table. That wouldn't be very impressive. It could take you ages, and as well, in about 20 odd steps, you've got 20 opportunities to make a mistake. So I'm not saying do it longhand. If you're in an exam and really stuck or pressured, you could just do 24, 48, 96 again and again and do it the long way, but I am not recommending doing that. The sophisticated way of doing it is to take logs of both sides. So, next step. So ln, take natural logs, or any log to any base, but ln is a button on your calculator. That's why I'm suggesting it. ln of 2 to the n minus 1 has to be just greater than ln of 100,000 divided by 3. This power can now be brought to the front. So n minus 1 lots of ln2 has to be greater than the natural log of 100,000 over 3. So expand this out, we get n times ln2 minus 1 times ln2 is obviously ln2. That has to be greater than the same thing yet again. Therefore, if we add ln2 to both sides and then divide by ln2, we can see that n has to be bigger than ln 100,000 divided by 3 plus ln2 all over ln2 which is, well, I do not know. This is why we've got one of these things called a calculator. So, ln 100,000 over 3 plus ln2 all divided by ln2, n has to be greater than 16.02. So 16th term won't quite be big enough. We need 17 terms. You can check this on your calculator. So 16th term will be almost 100,000 looking at this. So 3 times 2 to the power 16 minus 1, so in other words 2 to the power 15. Yeah, it's not quite big enough, so we need 17 terms, in other words 17 minus 1 power 16. Fudge that. What am I doing here? So 3 times 2 to the power 16. That's the first one to go beyond. So we need 17 terms. So therefore, the 17th term is the first to go above 100,000. Let's have a look at the next one. Worked example 3. So we're told here that the second term of a geometric sequence is 4 and the fourth term is 8. The common ratio is positive, we're told, so find the exact value of the 11th term in this sequence, giving your answer in the form k root 2, where k is an integer. So we need to remember what the nth term is. The nth term of any geometric sequence is ar to the power n minus 1. So we're told what the second term is. The second term is 4. The second term is ar to the power 2 minus 1, which is just a times r. So ar equals 2. We're also told the fourth term is 8. The fourth term will be ar cubed. So ar cubed equals 8. So if we put these two bits of information together, we can now find both a and r. So what we can do here is we can take one and divide it by the other. I do apologise, the second term here is 4, isn't it? Not 2, so I need to just scrub it off, I'm sorry. That's 4. Apologies. So I can now do ar cubed divided by ar. So if I do one of these divided by the other, a divided by a will cancel. R cubed divided by r will give me r squared. Then 8 divided by 4 is 2. R squared is 2. Therefore, the common ratio, which is positive, I just consider the positive root of 2. So r is root 2. So therefore, the 11th term is going to be the first term, a, but I don't know what a is. So what I can do here is go back to this. If I know r is root 2, I can sub that into ar equals 4. So if r is root 2, then a times root 2 is 4. So a is 4 over root 2, using the fact that we know r is root 2 now. And 4 over root 2, we can simplify. If you're feeling lazy, like I often do, we can use one of these. 4 over root 2, we'll get it into the exact form for you. There, 2 root 2. So the 11th term is going to be a, which is 2 root 2, times the ratio r to the power 11 minus 1. So that's 2 root 2 times root 2 to the power 10, essentially. Now, we can do this on a calculator if you want to, that's absolutely fine. In terms of understanding where the numbers are coming from, let's just try and do this manually. Root 2 squared is 2, and power 10 is something squared, then to the power 5 again. So if you think about power 10 as being something squared, then to the power 5, root 2 squared is 2, then do that to the power 5. And 2 times 2 to the 5 is 64. 2 to the power 6 is 64. So you've got 64 root 2. But again, at this stage, you could have just banged that into your calculator and it would have come out exactly as you needed. So 64 root 2. So in other words, k is 64 if you really want to say that. You don't need to. This is sufficient to pick up all the marks. Finally, worked example number 4. We've got the numbers 3, x and x plus 6, which are the first 3 terms of a geometric sequence, all terms being positive. So we need to find the value or values of x, and then b, the 10th term of this sequence. So we need to know that the common ratio is constant. So I've got 3 here, then x plus 6. So the ratio of x to 3 has to be the same as the ratio of x plus 6 to x. So x divided by 3 has to be the same as the ratio of x plus 6 to x. So this is an equation we can solve. It's a fractional equation, so we can cross multiply. There's a few ways of solving these. I was always taught cross multiplication works. Whichever way you want to do it, you should get the same result. So just keep an eye out and see if you agree with me. So x times x squared has to equal 3 times x plus 6. We can now expand this. 3 times x is 3x, 3 times 6 is 18. Get it all onto one side equaling 0, so take away 3x and take away 18. Gives us this. We can now factorise. So two numbers that multiply together to give minus 18 and add up to 3 are x plus 3 and x minus 6. So therefore x equals minus 3 or x equals 6. However, we're told all terms are positive, so x can't be negative 3, x has to be 6. Based off that, we can work out the 10th term. So now we know that x is 6, we can sub this into the sequence. So the sequence, the first term is 3, x is 6, therefore x plus 6 will be 12. So therefore the first term is 3, the common ratio is 6 divided by 3, which is 2. So the terms are doubling. So therefore the 10th term is the first term multiplied by the common ratio 2 to the power of 10 minus 1. So 3 times 2 to the 9 essentially. Then quick this one out. So 3 multiplied by 2 to the power 9 gives us 1,536. And then we're done. So now it's over to you to try some of these questions on your own. So, if you can turn to page 69 in your books, exercise 3C, and try these particular questions, try more if you can of course. Question 1, ACEG, question 2, ACE, question 5, question 6, then 8, 9, 10 and 11. Check your answers regularly using the back of the book. If you're not sure, ask me or a neighbour. If you're still really struggling, come and find me at lunchtime or even leave a comment in the comment section. I'll try and get back to you. Please like, please subscribe. Thank you very much for tuning in, and I'll see you all very soon indeed. Take care, and goodbye for now.